Hey everybody, we're going to start out this next video lesson by talking about how we measure energy. Now there is a unit that is associated with the measurement of energy, and it is what is known as the joule. Joule is the basic unit of energy. Now you might be more familiar with energy in the form of food. Now energy from food are called calories. And both of these are considered to be units of energy. But one is the old British system and the other is the metric system. And of course we're in science class, so we're going to use the metric system. Now if you want to know what a joule really is, it's the amount of energy needed to move a 1 kilogram mass 1 meter in 1 second. So basically, if you're holding a 1 kilogram object and you take one step forward in 1 second, you just exerted 1 joule of energy. To be honest, a joule of energy is a very small amount. And so in science, usually we measure our energy in kilojoules, or 1,000 joules is 1 kilojoule. Now how do joules relate to calories? Well, there are 4.18 joules in 1 calorie. And so that's the conversion between the metric system and the English system. But 1 calorie, and it's a little calorie, is actually not the same calories in the food that you eat. In fact, there are 1,000 little calories in 1 big calorie. Now these are the calories that are on the side of the food boxes that explain how much energy is in that food. So in other words, 1 calorie is 1,000 little calories, and there are 4.18 joules in 1 calorie. And if you're thinking about converting these, and it's easy to do using dimensional analysis, 1 calorie of food is equal to 1 calorie on the bottom and 1,000 little calories on top, and then 1 little calorie on the bottom is 4.18 joules. So 1 food calorie is 4,180 joules of energy. So in other words, a joule is a very small amount of energy, because just sitting in your seat, you're burning calories. Just sitting in your seat breathing, you're burning a calorie or 2 per minute. So you're burning 4,180 joules just sitting there for a couple of minutes. So we use kilojoules as a measure of energy, joules or kilojoules. Here are 2 more chemical reactions, and I'd like to show you a little bit more variation in types of reactions you'd see. This first one is one that's exothermic again. Anytime you see a delta H that's negative, then you know that the energy has been given off or released. Now, the other example is one that you're not likely to come across very often, but this is a chemical reaction that does happen. And notice that this time you have a positive energy, which means that this reaction absorbs energy when the reaction proceeds. Now, if your hands were the surroundings in each one of these reactions, if you hold on to this one, it's going to release energy to your hand, and it's going to get very, very hot. So hot you can't touch it. But this one, as the reaction proceeds, it's going to pull energy from your hand, where the energy is higher in the surroundings than it is in the system, and the reaction itself is going to feel very cold. Now there's 2 ways to identify the energy of a chemical reaction. Sometimes it's listed underneath or after the reaction, separated from the reaction by a semicolon or something like that. Like here, I've listed them underneath the reaction. But you can actually include the heat as part of the reaction, as part of the reactants and the products. And I'm going to tell you how to do that right now, because that's going to be more helpful for us when we're going to do stoichiometry on the next video lesson. So if delta H is negative, then negative delta H is exothermic. Exothermic can be treated as energy as a product. And so if I go and add this energy in as one of the products, I add 732 kilojoules of energy. The negative sign of the delta H doesn't go into the reaction. The negative tells you that it goes on the product side, but it doesn't go with it. The number 732 goes on, but not the sign. Again, the negative tells you which side of the reaction, products or reactants. Since it's negative, it's a product. Treat the energy as a product. And by contrast, if you've got a positive delta H, then you'll treat the energy as a reactant. And so I'll go in and add the energy as a reactant. It is 170 kilojoules of energy as one of the reactants. So again, in summary, if it's positive, you add it to the reactant side. If it's negative, you add it to the product side. But when it's listed in the chemical reaction, it's always a positive number. When it's listed separate as a delta H, the negative means that it's exothermic. The positive means that it's endothermic. And now that we've got energy listed as part of the reaction, either exothermic or endothermic, we can now do some stoichiometric calculations, which is something that I'm going to show you next. Here's another look at another chemistry thermochemical problem that has energy in it. And you know it's exothermic energy because it's negative, as you can see right here. So if I were to rewrite this reaction, where energy as a reactant or product, I'd add it as 56 kilojoules on this side of the reaction. If this sign were positive, it would go on the reactant side. But now we're going to talk about how you can use this reaction now with energy added as a product in order to do a stoichiometric calculation. Now this is stoichiometry, just like stoichiometry always has been. But instead of mass and moles, now we have energy. In traditional stoichiometry, the first step was going from mass to moles. In this case, you'd have 75 grams of a substance converting to moles. And you're going to do the same thing in the first step of this type of stoichiometry problem. If you remember anything about stoichiometry, it's this, that you should always convert to moles. Whatever you have to start should always be converted to moles. If it's already given to you in moles, then that's not a problem. But since we have grams, we should convert to moles. That's true of almost all stoichiometry problems. But it's this next step that makes it a little bit different from the traditional. Instead of converting from moles of known to moles of unknown, we're going to convert from moles of known to energy. And this shouldn't be a big deal because we know the energy in the reaction, and we can convert from moles of one of these to energy using a simple stoichiometric step. Let me demonstrate using this example up above. So like traditional stoichiometry, you start with your known of 75.0 grams of NaOH, and you want to convert to moles. 1 mole of NaOH on top is equal to 40.0 grams of NaOH. I added this number up off the periodic table. It's Na plus O plus H. Now next I'm going to multiply by a ratio, and again I'm going to put my moles of known on the bottom. Moles of NaOH. And I picked the number out of the balanced chemical reaction that matches the stoichiometric coefficient. And there's a 1, so I just simply put a 1 down here. It's not always going to be a 1. It might be a 1, but it doesn't guarantee that it is a 1. Now on the other side of this conversion factor is energy, because we're going to convert from moles to energy. So now I put in the energy on top, 56 kilojoules of energy. So as you can see, the only new step is instead of going from moles to moles here, I go from moles to energy, and in fact I'm done. These problems will never be more than this many steps. Sometimes it might be just a single step from going from moles to energy, or you have to go from grams to moles and then moles to energy. But I simply plug this into my calculator and figure out what the correct answer is. And the answer is 105 kilojoules. Now, I need to do one of two things in addition to writing down the number. I either need to add a negative sign, which represents energy released, because this was exothermic energy, and so the symbol needs to be 105 or negative 105 kilojoules of energy. Or I can say, using an actual word, released, add that to the answer. So I say 105 kilojoules released. Both are acceptable forms of the correct answer, but you need to signify that this energy is exothermic in one form, either by using a negative sign out in front or saying it's released. Here's another practice problem. This time the chemical reaction is not all in a 1-to-1 ratio, which is why I chose this one. So let's start, as always, by jotting down the known of 454 grams of magnesium to start this problem. And I'm going to convert to moles, because our first step in stoichiometry is always convert to moles. So by putting 1 mole in the top, I write down this molar mass of magnesium on the bottom, which is 24.31 grams. And then I'm going to go from moles of magnesium to kilojoules of energy, and I'm going to put in the stoichiometric coefficient in front of the magnesium, which happens to be a 2. And I'm also going to add the energy up on top of 1204. And I plug it into my calculator, and I get 22,500 kilojoules. That's rounded to 3 significant figures, because this first number is 3 significant figures. And again, I got to make sure that I either add a negative sign to represent the energy being given off, or I go ahead and add the word released, or another synonym of the word released, in order to determine or explain that this energy has been given off in exothermic fashion. If the energy term is pulled off the reactant side, then you would just keep this as a positive number rather than a negative number, and you would say this much energy added. But stoichiometry is a reversible process, and this second example is one where in fact that instead of starting with grams of a substance and converting energy, you start with energy of a substance and convert back to grams, because it says what mass of magnesium oxide could you make with this much energy. So I'm going to think about this process in reverse. I'm going to take the energy and convert to moles. So I begin with 7,500 kilojoules of energy over 1, and I'm going to put kilojoules on the bottom and moles on the top. It's the kilojoules to moles conversion, just inverted. I'm going to put 2 on top because it's the moles of MgO on top and 1204 on the bottom. So by doing that, I converted from kilojoules to moles of MgO. Now I can put the 1 mole of MgO on the bottom, which is the molar mass step, converting from moles to grams. So 1 mole of MgO, grams of MgO go on top, and I use my periodic table to add up Mg plus O, which is 40.31. Now I just need to punch these numbers in my calculator and come up with the correct answer. And the answer is 502.2 grams, which is 4 significant figures, because that reflects the 4 significant figures of the number I started this problem with. That takes care of this video lesson. Thanks for watching.